record this. So all those people in Auburn can watch it later. All right. A plane is flying at an altitude of 1 mile at a speed of this. It flies over a radar station. And we want the rate, the distance from the plane to the station is changing.
Is that like diagonal distance?
Yeah, that would be.
So you use like hypotenuse.
Mm-hmm. Mm-hmm.
Oh.
So let's see. We're going to have a ground. We're going to have the floor. The ground should be green. Okay, so there's the ground. Here's our radar station. I'll just put it, I don't know, we'll put it right here. So there's my radar station. And then we have a plane. Let me draw a plane. Let's see here. Let's see how well I can do here. Here's my plane. Thank you. Let's see, let's give it. It's a rocket. All right, so there's my plane. Let me make sure all that's one big picture. Oh, wow, that's a whole bunch of different pieces. All right, so we have a plane that's flying at an altitude of 1 mile, and it flies over a radar station. Were we able to get this drawn okay? And it flies over the radar station, then it's moving away from the radar station, and it wants to know the rate, the distance from the radar station. That's going to be linear. So we're going to go straight to the plane. We'll know the rate that distance is changing. And it is changing, and remember, related rates, anything that changes, we'll give it a variable. So I'll just call that d for distance. You could call it something else. Then we also know the plane is flying at a certain height, correct? Right, so we'll call that h. There's the height. What all do we know? Okay, what is h? Okay, h is 1. Is h always 1, or is it just for a split second? That's always 1. So instead of calling this h, let's actually just go ahead and put 1 there. Anything that's constant, we'll go ahead and throw the actual value in there to cut down on the number of variables. Are we good? So I know that that is always 1. What else do we know? Okay, the plane is flying 500 miles an hour. So the plane's going this way at 500 miles per hour. That is a rate. Yeah? That's going to be the derivative of something. What would that be the derivative of? Yeah, that's going to be this distance right here. Then he called it x. So we'll just call that x. You could also draw your triangle the other way, like this. But the dimensions would be the same, whether you draw it up here or down here. So dx dt is 500. That's how fast the plane's traveling. Are we okay with that? You okay with that? Are we able to pull everything together? All right, so that's 500. What else do we know? Find the rate at which distance is changing. What are we looking for? Uh-oh. What are we looking for? Okay, well, let's go on to, okay, when it is 2 miles away from the station, what's 2 miles? We're measuring the distance from the station to the plane. Which piece of that is in the triangle? That's D. The plane is not on the ground. This is not the distance from the station to the plane. The distance from the station to the plane is right here. So we're looking for, or we know that we're looking at a point in time when D is 2. Is D always 2? No, the plane's moving. It's not hovering. So D is not always going to be 2. So I'll kind of put that on hold. We'll plug that in later. And we're looking for the rate that distance changes. So we're trying to find d dt. The rate that D changes, that's what we're looking for. Do we have any questions there? Yeah? So that's all the information given in the problem. We've got to tie all of this together in some kind of a formula. What do you think we'll use? Pythagorean theorem. Everything we're given is dealing with the lengths of this triangle. We know nothing about the area, so we're not going to use area. I'm going to use Pythagorean theorem. X squared plus 1 squared is d squared. We good? Now what? Take the derivative. Yeah, that one's kind of finicky. Derivative of x squared is 2x dx dt. We good there? Good there. Plus derivative of 1 squared is 0. That's a constant. Equals the derivative of d squared. 2d. 2d dd dt. Yeah? So we take the derivative. After we set up the formula, we take the derivative. Now what? Plug in everything we know. And we're looking for dd, so this is my variable right here. That's what we're going to have to solve for, which means I need to plug something in for everything else. So 2 times x. What is x? Yeah, we don't know x yet, but we could figure it out because we're looking at a triangle at a point in time when d is 1, or when d is 2, that's 1, we're solving for x. We could just solve that with Pythagorean theorem. X squared plus 1 squared equals 2 squared. And x is the square root of 3. Yeah? Yeah? So when d is 2, x is the square root of 3. Do we know what dx is? 500, that was given to us. Plus 0 equals 2 times, do we know what d is? 2, very good. And dd dt is what we're looking for. Yeah? Yeah? Plug in, now we solve, divide by 2 times 2, and this thing would clean up to 250 times the square root of 3 equals dd dt. We just need units. What would units be? Miles per hour. It's the rate that the distance is changing. That distance would be measured in miles, and time is measured in hours. So there's your answer. What are we thinking? Making some sense? Maybe? Maybe not? Maybe so? Yeah? So that was 7. Any questions about there? Any questions about 7? Okay, what's another one we need? 15. All right. 15 looks scary. Well, let's see what's happening here. What about a boat? I think that boat actually goes with number 14. It is a boat. For some reason, that boat reminds me of Scooby-Doo. No idea why. Huh? Yep. All right, so here we go. At noon, what is noon? 12 o'clock. All right. Ship A is 100 kilometers west of ship B. So here's what I'm going to do. West is, we generally think of that as left, right? So I'll put A right here. And then 100 kilometers this way is ship B. So there's A, there's B. Are we okay so far? We good so far? All right. Ship A is sailing south. So ship A is going this way. Ship A is going south at 35 kilometers per hour. Yeah? And ship B is sailing north at 25 kilometers per hour. So ship B is going up at 25 kilometers per hour. Are we good? Yeah? How fast is the distance between the ships changing? The distance between two ships, I'm going to draw that in here. That is this distance right here. This one's a tough one. That's the distance that's changing. I'll just label that D for distance. Are we good? At 4 o'clock. Okay, what's changing and what's staying the same? Time is changing, right? So we know we have time, which it can't really label time in the figure, but time is changing. What else? Okay, what about the 100 kilometers? Is that changing? Huh? No, that's going to stay the same. Their initial points are going to remain 200 or 100 kilometers apart, right? So the east-west distance between them is always 100. Anything else? Okay. Yeah, the distance these two ships is traveling is increasing. Just to keep it consistent with the boats, I'm going to call this A and this B. Is that okay? Those distances are going to change. How fast are they changing? How fast is A changing? 35 kilometers per hour. That's how fast A is moving, right? So dA dt is equal to 35. dB dt, the rate that B changes, is 25. Yeah, I guess I need to put units in here. Kilometers per hour. Kilometers per hour. We good? What are we looking for? We're looking for dD dt, the rate that the distance between them is changing. So we're looking for that. Whoops. The rate that the distance is changing. That equals something. Let's see. Is that everything we have? We do know that they've been traveling for 4 hours. Is that right? But that's just kind of temporary. 4 hours, I mean, we're not stopping time. That'd be kind of cool if we could, but we're not. So we know they've been traveling for 4 hours. What all can you tell me now? Don't think calculus. Based on the information we know how fast they're moving, we know the initial positions and all this mess. There's one other piece of information. They didn't give it to you in the problem, but we could figure it out. Yeah, we can tell how far each one of them has traveled over those 4 hours, right? So if they've traveled for 4 hours, I can use that to say that at this point in time, at 4 o'clock, A is going to be... Y'all pretty smart. Y'all can figure this out. Are you punching that in the calculator, La Mancha? What? Okay, that's B. All right. So B. So you punched in 25 times 4? Or gum. All right. A is going to be 140. All right. And again, those are not always true. That's just kind of temporarily. That's not always true. But I know that A is going to be 140. B is going to be 100 at this point in time. Now, the tricky part is we've got to come up with some kind of a formula to tie all of this together. What do you think we're going to use? There are two triangles. Probably not. They might be similar, but I don't think they are. Hold on to that thought, Crane. Yeah. Did you hear what Crane said? He said, make it a big triangle. Instead of two smaller triangles, let's make it a big triangle. Crane, how are you going to do that? That's kind of weird. So what? Okay, so you're saying put the 100 down here and then move the A over here? Yeah, that's exactly what we're going to do. To make this a little bit easier to manage, rather than look at it as two triangles, I could take this distance right here and move that 100 right here. Is that okay? And then I could take this distance A. Where'd clone go? I lost it. There it is. And I could move A right here. Yeah? And when I do that, does my D change any? No, it doesn't. So we're still preserving the distance between the two boats, right? But by doing that, what I've done is I've turned two triangles into one big triangle, and now I think we can come up with some formula to tie all of this together. It's going to be the Pythagorean theorem. You're good? Where we're now looking at this big triangle right here. You're good? You're good? Questions, comments, concerns? Yeah? How am I going to set up the Pythagorean theorem here? 2/4. Oh. Okay, so you found that total distance, right? What's the danger in doing that? The thing is, A and B are changing, so you don't want to plug in your values for A and B yet. I like that you're adding them together because that's what we're going to need to do. But instead of plugging in 140 and 100, I'm just going to leave it as A plus B squared. Is that okay? That's this leg is A plus B. This leg is 100. Can I say 100? Why? Because that's constant. That's not changing. Anything that's constant, you can go ahead and plug in the number. Is D going to change? Yeah, it is. So we're going to leave that as D squared. Are we okay? Are we okay? There's our formula. There's our formula. Now what do you want to do? We're going to take the derivative. And we have to be careful here. How did you do the derivative of A plus B all squared? It's a chain rule. Y'all remember chain rule? What would the derivative of A plus B squared be? Bring down the 2. A plus B to the first, right? Then we need to multiply by the derivative of the inside, which is, yeah, and just make sure you put it in parentheses. dA dt, that's not an A. Let's try this again. Ugly, huh? dA dt plus dB dt. That's the derivative of the inside. You're good? So I've done the derivative of that first one. What's the derivative of 100 squared? 0 is equal to 2d dd dt. Are we good? Are we good? Now we can start plugging in everything that we know. 2 times what's A and B? Figure that up here. 140 and 100. Times dA, which is dA, 35. dB is 25. Is equal to 2 times what's D? Yeah, we're going to have to do the Pythagorean theorem to get D. We're solving for dd, right? So we're going to leave that dd. But to get D, I'm going to need to plug in my A and my B and solve up here. And we'll use the calculator for this. But that would be, what, 100 plus 140 squared plus 100 squared is equal to D squared, right? What is that? Does anybody know that? Using your little baby scientific calculator. Is it 260?
Yeah.
Oh, how sexy. I thought it was going to be something ugly. Well, then your little baby calculator is going to be okay. So we get D is equal to 260. I was anticipating something ugly, like the square root of something weird or some funky decimal. If that were to happen, then you would need to make sure you use the exact answer, and that's why I was scared of you using that scientific calculator, because it would give you a decimal. So you would need to either store that answer or make sure you use the exact square root answer. So D is 260, so I can plug that in over here now. And then we will solve for dd dt. Yeah, so that'll be 2 times. Now I'm pretty smart, so I'm going to go ahead and say 140 plus 100 is 240. And 35 plus 25 is 60. And we'll divide that by 2 times 260. And that is my dddt. 87 point what? 807 point, give me 3 decimals. We always do 3 decimals. 692. What's my unit? Kilometers per hour, because d is a distance. We would measure distance in kilometers, and my unit of time is hours. Which really, you could leave it like that, huh? Mm-hmm. Are we good? We good? Shaky, huh? At least 1, maybe even 7. I was playing Words with Friends with somebody, and I used Jags as my word, and they missed it. What was the Spain Park student, too? Yes? The reason they're both positive is because they're both getting longer. If A was shrinking, and I could have, and there's actually one problem in the book that's very similar to this, where what's actually happening in the other problem is you've got one common point, and what happens is like ship A starts by moving south. And so if ship A is moving south, that distance, dAdt, would be something positive because that length is getting closer. But what's happening on the other end is there's a ship B that like starts over here, but is moving towards that. So that length of the triangle, as time moves on, B is going to move a little bit closer, and this distance is going to get shorter. So in that case, dB would be negative because the length of the triangle will be getting shorter. So yeah, you just have to think, is that dimension growing or is it shrinking? And that. Oh, really?
If you think about it,
That is kind of fast, right? Because the total rate between them, yeah, they're only moving 35 and 25 kilometers. Oh, jeez.
35 times 25 instead of 35 plus.
Holy cow. Really? Really?
Because 60 times 480 is 20,800.
Okay. It is 55.385. Goodness, La Mancha. So warp speed, what'd I say? 55.385.
4 hours, A got 140 kilometers, B got 100, so 4 hours are only 2/3. Calculate.
And that's a good reason you don't simplify your answers too, when you don't have to. Oh, we good on 15? You good on 15? Any other questions on that one? Do we need another one? 5. The snowball. Never really got that gross. All right. Number 5, a snowball melts so that its surface area decreases at a certain rate. Now, you probably had to do some fishing to get the surface area of a sphere. Do y'all know what it is? It is 4 pi r squared. That is a formula for the surface area of a sphere. I will give you things like that. Now, Pythagorean theorem, area of a triangle, area of a circle, area of a square, things like that I expect you to know. But when it comes to 3-dimensional shapes, I'll give you those formulas. So that's the formula we're using for the surface area of a sphere. Okay, what all do we have here? What do we know? Okay, diameter is Okay, it's 2r. I agree with that, right? And we also know that the diameter is 10. Is the diameter always going to be 10? No, snowball's going to melt, right? So the diameter will decrease. It'll get a little bit smaller as we keep moving. All right. What else do we know? Yeah. dA dt, the surface area, and I suppose you could have called it S also. I just used A. dA dt, and the surface area is decreasing. So this is a case where your rate will be negative, and my units are centimeters squared per minute. Are we good? Are we good? All right. That's everything, isn't it? What are we looking for? What's the unknown? dd. We're looking for the rate, at which rate is the diameter decreasing. Or so let's find the rate at which the diameter decreases. We are looking for dd dt. Yeah? So what do you think we're going to do here? Yeah, the problem, we could go ahead and differentiate, which if you did, what would the derivative be? I'm going to erase this, by the way. dA dt would be what if I did the derivative from here? Yeah, I like to leave the constant 4 pi alone, so it'd be 4 pi, and the derivative of r squared is 2r dr dt, which is very good. That is true. What's the problem with that, though? Yeah, it's not in terms of diameter. It asks you questions about the diameter, and it gives you information about the diameter. So we're going to need to somehow work diameter into this, which I could still do from this derivative, but it's a little bit easier. And this is kind of like what we did yesterday. There was a problem where if you did the substitution at the beginning instead of at the end, it works a little bit easier. So what would I substitute here? What could I do? Yeah, we know that r is the diameter divided by 2, so I'm going to plug that in for r. So my area, surface area, is going to be 4 pi, and instead of r squared, d over 2 squared. Okay, good? Okay, good? Now what? If you square it, this turns nice. 4 pi d squared over 4, right? And what happens with that? You just get pi d squared. So my surface area goes from 4 pi r squared to just pi d squared. Yeah? Now I would do the derivative. Now that I have it in terms of diameter, which is what I need because it asks us for diameter, I will do the derivative. What's the derivative of pi d squared? Pi times, and the derivative of d squared is 2d, 2d, dd dt. You're good? Okay, good. Then once you take the derivative, now you start plugging in what you know. Do I know dA? It's -1 equals pi times 2 times, do I know d? D is 10. They gave us that. Times dd dt. I don't know that because that's what we're looking for. And what do we get for dd? -1 over pi times 2 times 10, which is 25. We good? We good? We good? I do need units. Oh. Yeah. What would my units be? How do you measure diameter? Yeah, but what's my unit? We have units. What's centimeters, right? Diameter is measured. That's a linear measure. That's not an area. So centimeters per, and my unit of time is minutes. Somebody said seconds earlier. We're doing minutes here. You good? Got to make sure you keep the units right. How are we feeling? Is 5 working okay? Is 5 working okay? Questions, comments, concerns, thoughts on life? Any other homework questions? Any other homework questions? No. No. All right, here's what I want to do. I want to do one problem. This is great because now y'all are going to be like ahead of everybody else, and we can just like say, ha, suckers. Y'all are going to be smarter. Not that sheet, it's on the back. I need to open up the back. Oh, no, that's not what I want. Go away. Go away. Recent, related rates more. Number EX3. When the rocket is number EX3. Yep. Oh, wait. Oh, jeez. I forgot that when I'm recording it does these stupid lines when I... Oh, well. You can still read that, right? All right. EX3. Let's see if we can draw this. A camera is mounted 3,000 feet from the base of a rocket launch pad. So we will have a ground. We have a rocket launching on one end. So we'll say the rocket's taken off here, and the camera is right here. And the camera is 3,000 feet away. I don't think that's going to change. We can always go back and fix it if it is. Okay, the rocket launches and rises vertically. So our rocket will take off vertically. Yeah. So there goes our rocket. And it ascends at 880 feet per second. When the rocket is 4,000 feet away. How fast is the camera angle of elevation? Ooh, so the camera is tracking the rocket, right? So the camera is going to start following the rocket down here, and then it's going to follow it, and the camera is going to move up, right? Right? And it's talking about that elevation angle. Where's the elevation angle? Y'all remember this? Remember Miss Culbert's class? Or Miss Hawkins, or whoever y'all had? Where is the elevation angle? Yeah, that's one over here by the camera. This angle right here. So we're talking about that angle. How fast does it have to move to keep the camera aimed at the rocket? All right, so let's pull out all the other information. I left out some stuff. We have 3,000, and I labeled the angle. What else do we know? Huh? Yeah, the left leg is changing, so I need to call that something. What do you want to call it? X. Okay, so that leg is changing. It is growing. The rocket is ascending at 880 feet per second. Are we good? Yeah. And we are looking at a point in time when X is 4,000. Is X always 4,000? No, so I'm not going to plug in 4,000 yet. I'm just going to make a little note that at some point in time, X is going to be 4,000. How are we feeling? How are we feeling? All right. How fast is the camera angle of elevation changing? What does that mean? It's d, not d of, just d theta, but yeah. So d theta dt equals something. That's what we're looking for. Have I gotten all the other information? I've already labeled the 3,000 feet. Is that changing? No, so we can keep that at 3,000. Anything that's constant, leave it in as a number because it makes it just a little bit nicer. All right, we've got to come up with some formula to tie this together. What do we think? Yes. Now, we're asking a question about an angle. That means Pythagorean theorem isn't going to help us because Pythagorean theorem doesn't use angles at all, right? Basically, you just have to know that there is a right angle, but the 90 degrees is not part of the formula. So I need to tie in an angle, which means we're going to have to use trig. And we could actually use several things, but I'm going to go with tangent. Tangent of theta is opposite over hypotenuse, x over 3,000. Are we good? That's the formula we're going to use to tie this together. Now what? Find the derivative. Find the derivative. Okay, somebody other than William. What's the derivative of this? Secant squared. Y'all remember that? Derivative of tangent is secant squared. Okay, keep going. You could do quotient rule. Oh, and do product rule with that. Can somebody make this a lot easier? Yeah. X over 3,000 is the same as 1 over 3,000 times x, right? What would be the derivative of 1 over 3,000 times x? 1 over 3,000. Now, the only time you have to do the quotient rule is if you are dividing by a variable. If there's a constant in the bottom, then you don't need to do quotient rule. Not that it won't work, it's just making things unnecessarily difficult. The derivative of x over 3,000 is 1 over 3,000 times dx dt. Are we okay so far? Yeah, we forgot the left side. We did the derivative of something with theta. We need to put in d theta dt, which we would have run into a problem because we've already decided we need to solve for d theta, right? And when you realize we didn't have a d theta, hopefully that would have let you know something screwy is going on. All right, so now we have to start plugging in what we know. We have secant squared theta. I'm actually going to change that to secant theta squared. Is that okay? It's the same thing. I just want to write it like this. D theta is what we're solving for. Is equal to 1 over 3,000. Do we know what dx is? That's 880. We do need to solve for d theta. The problem is we need to do something with this secant of theta. And we cannot use a calculator. Okay, secant is 1 over cosine. I agree with that. It's a reciprocal of cosine. How does that help us? What would y'all have done had I not said, like before I said you can't use a calculator, and I said that for a reason, what were y'all thinking we were going to do? Or were you? Yeah, the very first time people do these, they want to actually find the measure of theta at this time, which you could do. But you would need a calculator because this is not going to be a nice angle. This is not like a 30, 60, 90 triangle or something like that. It's going to be some ugly decimal angle. What I'm going to do is instead of actually finding the angle, you remember the very first time y'all learned about trig functions? Way back in the day. You learned it as SOHCAHTOA. Yeah? She's the Native American who helped Lewis and Clark on their journeys. Some old hippie came along here tripping on acid, or taking our acid. That works too. Or sometimes oranges hate cabbage and hate tomatoes on acid. That works too. Anyway, okay. Okay, instead of finding the angle, we know that secant is the reciprocal of cosine, right? So I'm looking at the ka part of SOHCAHTOA. Yeah? And what I'm going to do is I'm going to find cosine that way. Instead of finding the angle, I know that cosine is adjacent over hypotenuse. Do I know the adjacent side for theta? It's 3,000, right? Okay, I know that x is 4,000, right? Do I know what the hypotenuse is? What would it be? 5,000. This is a 3, 4, 5 triangle. I just multiplied everything by 1,000, right? So since I know the side lengths of my triangle are 3,000, 4,000, and 5,000, then I know that cosine of theta is, what would cosine be? 3/5, right? Which means secant is 5/3. Okay, yeah? So instead of going through and finding the angle, we're just going to solve it in terms of the ratio of the side lengths. It's actually a lot easier than having to go through and get the angle, I think. You just don't think about it the first time because it's been so long since you've done trig angles like that, trig stuff. So 5/3 squared d theta dt is equal to 880 over 3,000. Yeah. And then solve for d theta dt. That's supposed to be a t. Holy cow, what is that? So d theta dt is going to be, let's see, what is 5 over 3 squared? 25 over 9. So I would multiply by 9 over 25. Is that right? So 880 over 3,000 times, and we'd multiply by 9 over 25. Are we good? Are we good? Tricky, huh? What do we think of that? What? Who? Where? .1056. Yeah, somebody verify that. This is what happens when you use your little baby calculators. I don't understand why y'all use those. Yeah, except if you punch in a fraction wrong, you can't tell because it doesn't display it as a fraction, like you did on that last one. Actually, that was an addition problem. That wasn't a parentheses problem. Anyway, we are leaving out units here. We're leaving out units. What are the units for this? What are we measuring? We're measuring an angle, right? How do you measure angles? No, this is not physics. Radians. Radians per, and my time is measured in, what was it? Seconds. Are we good? Are we good? So make sure, just remember that anytime we do angles, we have to use radians. Degrees are not real numbers. Y'all know, y'all remember when you learned all those different types of numbers? You had real numbers and complex numbers and all that. Degrees are not considered real numbers, so you can't use those in math. You have to use radians. I don't know. I'm not sure. Yeah. All right. Let's see. 1 minute. Oh, I wasn't going to do another problem. Y'all do the homework tonight. When do I see y'all next? Thursday? All right. And I'm gonna save this video and put it on YouTube so all those people who are gone can be excited and see what we did online. Isn't that wonderful? Why? Well, then come Friday. I don't care.